Hello, this is Walter Schneider from the University of Pittsburgh, and I will be providing a tutorial about information related to the brain fiber tracking competition for the IEEE International Conference on Data Mining, done by the Pittsburgh Brain Competition. And what we'll do is talk about how to segment the brain into fiber tracks. For information, go to the web links below. If you want to see this in high definition, you might click the HD button. This is a micro course on white matter tracks to assist your efforts to map the human brain connections based on the fiber data. As the micro course, what we're going to do is provide you a brief introduction to brain connectivity and high definition fiber tracking methods, a brief understanding of how the data were collected, key domain information to aid you for effective data mining methods, provide perspectives on the value of track segmentation. Note, it is not our goal in this micro course to provide you in-depth understanding of the imaging methods, to detailed data mining methods. You can do that by the readings which are provided. Will in this give you, this is in two parts. The first part is the introduction to high definition fiber tracking, what was collected and what did the data represent, and then a tutorial on brain neuroanatomy within that process. And then in the second video, we'll continue that process. So let's start with a brief introduction to high definition fiber tracking. What we do in higher definition fiber tracking is we use an MRI machine. We collect, in essence, the spin of water molecules and use that data to plot the diffusion. We plot that diffusion in 515 directions for different lengths of diffusion and different directions within that set. Based on that, we then create a diffusion spectra at each location in the brain. What are the directions that we have molecules diffusing? And that way we can see whether there's a single direction, which would be the case of a single fiber tract, or two directions if we have two fibers crossing. Based on that, we then create streamlines of information to identify the fiber tracks, and that's the underlying data of this competition. This illustrates how we are using deterministic fiber tracking in these methods so that we identify a start point, a seed point in the set of tensors for the fiber direction. We then move that pointer along, connecting those pointers to create a fiber link. I note we are not tracing axons, we're tracing fiber pipes. And a 1 millimeter fiber pipe is approximately estimated to be 40,000 neurons. Now let's provide a brief tutorial. I note that the brain has 140 kilometers of fibers in your head. These fibers appear in bundles or tracks. So to put this in perspective, it's like an aircraft cable where you would have a large bundle of fibers and individual drop points for the individual instruments. What we'll be looking at is individual tracks. This shows, for example, the arcuate fasciculus, where we have these individual points which are contacting particular pieces of cortical tissue. On the right you see in red the arcuate fasciculus, and then the other colors of other fiber tracks that are part of the competition. Now let's do a little bit of a tutorial on neuroanatomy. We're going to use the arcuate fasciculus as our example. Generally, you start at the surface of the cortical surface, so the fibers are popping through to the top surface, for example, of the brain. Then they converge from multiple sources, gathering into a large fiber bundle or cable within that set. Then typically they travel for some distance in this cable mode, and then will at the end again splay out to the different locations within that set. So this is an illustration of a sample fiber track. I note that the shape of the bundles can change. In the case of the arcuate fasciculus, it's sort of like a ribbon cable, but it deforms as it goes around other structures. So one must not assume that it will have a constant shape throughout its course. Also, fibers cross. That is, multiple fiber bundles might intersect as they cross through a piece of structure. Finally, there are between hemisphere and between brain variations of typically about a centimeter or two, so that, as illustrated on the left-right arcuate fasciculus, they're slightly positioned in different locations, and when you go from one person to the next, you might see a very substantial change in the specific locations where the cables end. The brain or the cortex is a surface, and from individual to individual, things move around in their position. The cables are probably going to the same effective place, but because it is a flexible circuit board that gets shaped from individual to individual, it may be in a slightly different location. It's useful to know how our expert created the fiber tracks that are the basis for this competition. The typical process, our expert Juan Fernandez-Merende created these fibers, included first using his knowledge of what the fiber tracks would look like. That's based on dissection knowledge, where he has dissected cadaver brains, and we have an expectation that it should look as illustrated by this shape. Then what he does is iteratively he places balls as to where the fibers are expected to go and where they should not be. So we'll go through this as an example. The first thing is the expectation. In this case, that we would expect about 1% of the brain fibers to be the arcuate fasciculus, 2,800 fibers of our set. Then identify the center of mass of where we expect that fiber path to go through, and create a ball that's, say, 2 times the size of the expected fiber path, so that we'll be sure to reach it. Then typically identify termination balls where you expect these fibers to pop out and end within that process. And you tell the system now to do an AND of those operations. And noted, we started from 300,000 fibers. Then with the first ball, we went to 67,000. The first termination ball to 5,000. After the second termination ball, we're down to 2,893 fibers. Note, we also have fibers that are erroneous within that set. So our expert would typically then identify some knot balls, as illustrated by the red ball here, and that would exclude those fibers from the set where they don't match the known physiology within that process. This is the arcuate fasciculus growing. You can see the fibers expanding and the start points being generated as the fiber set expanded. Now we're shifting to a 3D rotation where you see the fibers poking through the cortical surface, and then we'll tip that to just sort of see the position of the fibers. This is an example of overexpansion of the fibers. So as the seed growth now goes over, you see other fiber tracks being brought into the mix of fibers identified. So this ends the first part of the tutorial, and you can shift to the part 2 if you'd like more information about the challenges of the data and the resources. Thank you.